So now for our final idea of gravity slash projectile motion. Now this builds on the idea that the position function, when you take the derivative of position, it gives you velocity. When you take the derivative of velocity, it gives you acceleration. So we're building on that idea and applying it to problems that are thrown or dropped. So in other words, objects that have an effect due to gravity. So the position function for an object that is thrown or dropped is s of t is equal to negative 16t squared plus v naught t. So this is a v with a subscript of 0. Sometimes we say that's v naught t plus s naught, where s of t is the position at time t in seconds. So v naught is the initial velocity in feet per second. S naught is the initial position. Now the position function is s of t equals negative 49t squared plus v naught t plus s naught when v naught is in meters per second. So notice the only thing that changes in feet and in meters. So in feet per second, we have that coefficient of a negative 16. In meters per second, we have that coefficient of a negative 4.9. Can you figure out where that coefficient comes from? Well, that coefficient really comes from the acceleration due to gravity. Because now I know that when I take the derivative of position, it gives me velocity. So let's find that derivative. Velocity is equal to this derivative. So negative 16t squared, the derivative is negative 32t plus derivative of v naught t, remembering that I'm taking the derivative with respect to t, is just v naught. Finally, the acceleration, I get the acceleration if I take the derivative of velocity. So if I take that derivative of negative 32t, I get negative 32, and v naught is a constant, so that derivative is just going to be 0. In feet per second, I have the acceleration due to gravity, the acceleration due to gravity of negative 32 feet per second squared when I'm working in feet. In the same way, if I can imagine that I took the derivative of this position function and then I took the derivative again, in the same way, can I see how this 2 would be multiplied by negative 4.9 to give me negative 9.8? And then my acceleration would be negative 9.8. So in meters, I'd have that acceleration due to gravity of negative 9.8 meters per second squared. This is kind of the one we might be more familiar with from a physics class. All right, so these are our two formulas, and you'll be given an actual formula for the specific position function for that object based on the initial velocity and the starting position. When discussing projectile motion, there are two things to remember concerning our equations. Number one is that we're talking about the vertical velocity of an object. When we throw something, horizontal motion and vertical motion are independent, so we're only worried about the vertical velocity because the only thing we're really worried about is we want to know how gravity is affecting this object. So we're looking at that vertical velocity and acceleration. The second thing is that wind resistance is not part of the equation. So we're pretending like this object is being thrown in a vacuum, just for simplicity. All right, so with that, let's do an example. If a ball is thrown upward with a velocity of 160 feet per second, then its height after t seconds is s equals 160t minus 16t squared. Now, if we were asked what do these coefficients mean? Well, this 160t means my initial velocity is 160 feet per second, which we're given in the problem. Now, what's my starting point? I don't have a constant at the end of this, right? And so that tells me that the initial position is 0, meaning the ball is thrown upward from ground level. Okay, So we've got this equation for position. When does the ball reach its maximum height? When does the ball reach its maximum height? Now I could do this in a few different ways. I know based on this equation that this is going to give me a parabola that's opening downward because of this negative 16t squared. I could try to find the maximum of that parabola, but I know derivatives now. Here's what I'm thinking. The derivative of position is velocity, and we said that if I have an object that's moving in one direction and then it starts to move in the other direction, there's a point at which that velocity is zero, right? So when I'm just talking about the vertical velocity of an object and I'm throwing it up, there's a point at the very top when it's neither going up nor falling back down. And so to find where the ball reaches its maximum height, or when the ball reaches its maximum height, because I want a time that the ball reaches its maximum height, I'm setting the velocity equal to 0. That's going to be the maximum height. So I need to find that velocity, and so the velocity function I can find by taking the derivative of position. Derivative of 160t is 160. Derivative of negative 16t squared is negative 32t. Negative 32t. And so now I'm setting this equal to 0. And so I've got 160 minus 32t equals 0. So I want to solve for t. I can bring this 32t to the other side to get 160 equals 32t. And finally, dividing 160 by 32, I get the t is equal to, and this is going to be a 5. T is equal to 5. And because t is in seconds, t is equal to 5 seconds. So this is when the ball reaches its maximum height. Now, what is the maximum height reached by the ball? Well, if I've got a time, I'm given this position function that tells me the position at any given time. And since I know that I'm only worried about the vertical position, essentially that's going to give me the height. So I'm just plugging this time t into this position function to get that s of 5 is equal to 160 times 5 minus 16 times 5 squared. I can do this in my calculator. I get 160 times 5 minus 16 times 25. And I get 400. I get 400. And so this is 400. And I know I'm working in feet per second. And so the maximum height reached by the ball is 400 feet. So 400 feet off the ground. Next, what is the velocity of the ball when it is 384 feet above the ground on its way up? Okay, so I need to know the velocity of the ball when it's 384 feet above the ground on its way up. The first thing I need to know is when is the ball 384 feet? High, really. And so I need to find the time at which the position is 384 feet. In other words, I'm setting this position equal to 384. So I've got 384 equals 160t minus 16t squared. And I want to solve for t. So if I want to solve for t, now I can do this in a few different ways. Let me get this 384 on the same side as everything else. And I'm going to order these from highest to lowest degree. So negative 16t squared plus 160t minus 384 equals 0. Now I notice that a 16 goes into all of these terms. So I can factor out a negative 16 because I want to solve this quadratic. And I am left with t squared minus 10t. 384 divided by 16 is going to be, this is going to be a positive 24. And this is equal to 0. And so now I want to see if I can factor this quadratic. This gives me a negative 16 times. So can I factor this quadratic? Let's see. My first term is going to be a t. Now, are there two numbers that multiply to give me 24 and add to give me negative 10? Yes, negative 6 and negative 4. Now, this is important. If this cannot be factored, how else do you think I could solve for t? I could also solve for t by using the quadratic formula. I could use the quadratic formula to solve for t. But this one I could solve for by factoring. So when I set t minus 6 equal to 0 and t minus 4 equal to 0, I get that t equals, and I'll just put these in order, t equals 4 seconds and 6 seconds. So now I need to determine when it's on the way up. Now, a positive velocity generally means an object is going up, and a negative velocity means it's coming down. So if this is a parabola opening downward, I can assume that it's going to be going up before it's going back down. So let's see if plugging 4 into the velocity function will give me a positive velocity. So I'm going to test to see if v of 4 is positive. So plugging in 4 to that velocity function, I get 160 minus 32 times 4. 32 times 4 is 128, and 160 minus 128 is just going to be 32. And so this is going to be 32, positive 32, great, meaning this object is on its way up, feet per second. 32 feet per second. All right, and one more. What is the velocity of the ball when it hits the ground? So this function does a lot of good stuff. So it gives the position at any point. Let's look at this velocity function. This velocity function of 160 minus 32t. So when t gets really, really big, this velocity is just going to become a really, really big negative number. In other words, this velocity function doesn't know when the object hits the ground, it turns into a velocity of 0. But the position function can tell me when the object hits the ground because the ground is at a position of 0. So to find the time at which this hits the ground, I'm just going to set this position function equal to 0. And so I've got 0 is equal to 160t minus 16t squared. So this is going to tell me when the ball hits the ground. So on the right-hand side, I can factor out, let me factor out a 16 and a t. So factoring out a 16t, I'm left with 10 minus t. So using the zero product property, I've got two equations, 16t equals 0 and 10 minus t equals 0. 16t equals 0, okay, obviously this is going to be a t of 0, and 10 minus t equals 0, I get that t is equal to 10. Now because my time is in seconds, what does this tell me? This tells me that my ball has a position of 0 at t equals 0 seconds and at t equals 10 seconds, which means that it's being thrown up at 0 seconds and it's hitting the ground at 10 seconds. So to find the velocity at t equals 10, I'm going to plug 10 into that velocity function, and I get v of 10 is 160 minus 32 times 10. 160 minus 320 is negative 160. This is going to be negative 160. Negative 160, and my units are in feet per second. And so this is going to be the velocity of the ball when it hits the ground. And it makes sense that my final velocity is going to be negative because this ball is moving downward. All right, so that is it for our lesson on rates of change in the natural and social sciences.